Thank you guys, active listening again. Nice and quiet in 3, 2. So, elementary particles do make bigger things, obviously. I've already told you a couple of times that the up and down are responsible for making protons, neutrons. But there's a lot more to it. There's a lot more particles that get made. A lot of them are unstable, and actually there's probably an infinite number of combinations and ways that you could combine particles and antiparticles that aren't the pair antiparticle. So like you could take an up and an anti-charm, and you would get something with a charge of 0. It wouldn't annihilate because, yeah, they're opposite charges, but they're not the antiparticle of each other. So they would just make some particle. It would probably be unstable. And again, it depends on flavors and colors and all sorts of things. But they wouldn't annihilate. So you could make a theoretically infinite combination of trying to think of a better word than particle, of subatomic particles like protons, neutrons, and the stuff we're about to talk about. You could probably make a million combinations, but here's some common things. So anytime you take elementary particles and you stick them together, you make hadrons. Now, there's a word I want to use here. Hadrons are particles comprised of multiple quarks. Again, there's probably an infinite number of hadrons that may or may not exist, and some may be stable, some may not. Here's the 2 types that are most relevant to us. Mesons, which are combinations double check. I don't know a better way of explaining that wording, but it's a quark and an antiquark. It's just not this quark and its antiquark, because again, that would annihilate. So you can put an up and an anti-strange, and that's fine. You cannot put an up and an anti-up together. That would annihilate, okay? We'll bold that. And then the other thing is baryons. Combinations of 3 quarks or 3 antiquarks. That's it. Sorry. Is that better? Is that better? Let's do it this way. Bad. Sorry. Carry on. Right. Yes. Absolutely. Moving on. Check for understanding. It was a good one. It's a shame you missed it. If only you weren't distracted by a friend doing something inappropriate. You're probably going to fail this check for understanding now. 1 is no. Decide, making these up. If the following composite particles, let's use that word, are making a meson, a baryon, or nothing. I don't need a 1. There's only one question. A. U and U bar. Decide if that is a meson, a baryon, or nothing. U, U, D. No. Leave it at that. Is that nothing? Yeah, right. It's fine. It can still be considered a baryon by the definition I've given. It's just not a proton. Something else. It falls into the category of baryon. It's probably unstable because the charge is what, 4/3 and 1/3, 5/3 or something like that. Up, up, up. 2/3, 2/3. Down is -1/3. The whole positive. Is that not a proton? Yeah, that's a proton. Yeah. Oh, I meant to do a C on the E. Sorry. Meant to be a C. Ready? Cody. Question A. Meson, baryon, nothing.
Nothing.
Meson? You said nothing. Why nothing? They are antiparticles. They should annihilate. There is a complication here. Again, it relies on color and it's not assessed. But technically, a common meson is, we're going to look at it in a second, eta C, pion, eta C. Eta C, it's actually quite common, and it is a charm and an anti-charm. And the reason it can work is because it isn't opposite flavors. So even though it's a particle and it's antiparticle, they can be a certain type, sorry, not flavor, a certain type of color. So it can actually come down to color as well. And so sometimes an up and an anti-up can make a meson. It probably is unstable, but it can happen. I would accept nothing, annihilates. Or, if you want to get technical, it can actually make a meson. So either answer. No, they don't taste like anything. Taste and color has no concept here. We are way too small. B, please. Michaela. Baryon, absolutely. In fact, it's a proton. Sam, C. Baryon, absolutely. 3 antiparticles, they're fun. Probably not stable in that instance, as far as I know, but Nicola? D?
Nothing.
Nothing. If it was a meson with a quark and an antiquark in a pair, only 2, it would be a meson. But there's 3 particles there. They are not all quarks or all antiquarks. There are 3 things there, but 2 are quarks, 1's an antiquark. That's not a thing. And lastly, Max, E. That would be a meson. Absolutely. Cool? In the weird case of A, where you have an up and an anti-up, when they do make a stable meson, they're their own antiparticle. Again, I don't think this will ever come up in any of your assessment, but if you have an up and an anti-up making a meson, and you have another up and an anti-up making a meson, it's guaranteed annihilation if they meet. You can't then somehow stick them together. Which brings us to this, the common hadrons. Now, I'm not going to get you to copy this down yet. We are going to use this for a card game. The card game will play like this. You will get your quarks and your antiquarks, and you will also get gluons. You can use one gluon to make either a meson or a baryon. You need the correct quark and antiquark for a meson, or 3 quarks or 3 antiquarks for a baryon. I don't care what you make. It doesn't have to be anything fancy. I'm not going to accept... sorry? No, so the way you're going to play, and I'll be honest, kind of making this up on the spot. I've never played this game before. It's probably going to be the most difficult card game you've ever played in your life, but I think it could be a bit of fun. Have you ever played, I can't even remember what it's called, but you get the little tiles and you lay the tiles down in front of you when you make matching sets? What is it? No, not dominoes, no. Huh? What'd you say? I think it's like that. I don't know Mahjong. Anyway, basically what you're going to do is you're going to be in a group of 2 or 3, and you're going to get a few cards. There's going to be a deck in the middle. You're going to take turns picking from the deck. When you have a set, you can put your set down. You cannot, no, not exactly, no. You cannot have more, so you're going to start with 7 cards. You cannot have more than 11 cards. So if you get to 11 cards, you start discarding cards, okay? Now, if you make a set and lay it down, you get points based off the mass. If someone makes the anti-particle of yours, they can annihilate your set and take your points. They annihilate each other, but they get to claim the points. So at the start of the lesson, I want you to sort them, and I'm going to need you to sort them again because I have 4 decks in there. So